Welcome back, everyone. Consider acetic acid. Number 1, draw an appropriate Lewis structure, and number 2, identify the type of orbitals used by each carbon atom for bonding and estimate the bond angles around the carbon atoms. Let's begin with the first part of the problem. As the problem suggests, we have an acid. It has a carboxyl group, COOH, so we can simply begin by drawing carbonyl, carbon-oxygen double bond, followed by OH, hydroxyl group bonded to the same carbon. So that's carboxyl group, which is present in any acid. And the carbon atom is also bonded to CH3, given to us in the formula. So we're going to draw carbon with 3 hydrogens. We want to make sure that each carbon has 4 bonds. This is the case. We also want to make sure that each oxygen has 2 bonds. This is also true. And 2 lone pairs based on the octet rule. So we're adding 2 lone pairs for each oxygen. Each hydrogen is going to have a single bond. So we have the Lewis structure. For number 2, before we begin, we have to understand the hybridization of each carbon. For the methyl group, the hybridization is going to be sp3. That's because it has 4 electron regions, simply speaking, 4 single bonds. And the second carbon is going to have an sp2 hybridization. This is because it has 3 bonds, 2 single bonds and 1 double bond, right? So these hybridizations tell us the geometry around each carbon. For the sp3 hybridized one, we're going to have tetrahedral. And for the sp2 hybridized one, we are going to have trigonal planar based on the VSEPR theory. So now we can correctly draw the structure with the appropriate bond angles. For the trigonal planar geometry, we're going to identify the correct angles as follows. So we have COOH, and now we want to draw CH3. Now, CH3 is tetrahedral, so essentially what we can do is basically draw 2 solid lines, and then we can draw 1 carbon-hydrogen wedged bond and 1 dashed bond, which is pointing away from us. Let's assign all of the hydrogen atoms. That's our structure. It is not a Lewis structure, right? For number 2, we can use a simple structure which does not necessarily need lone pairs or all of the bonds expanded. Here we are simply interested in the types of orbitals. So let's begin with the carbon atom coming from carbonyl. Every single bond is going to have the same hybridization as the carbon atom itself. Essentially, we're going to use the same orbital, that would be more accurate to say, for the overlap. So when we consider our sigma bonds, those would contain the sp2 overlap. We're going to say sp2 for the carbon-oxygen overlap. Then we have the carbon-carbon overlap, which also involves an sp2 orbital. And now we have to be very careful. Essentially, we have our double bond, right? So the double bond contains an sp2 overlap for the sigma bond, but for the pi bond, it contains a p orbital, right? Which is not hybridized. And this is really important. We have to recall that double bonds, they consist of sigma and pi bonds. For the other carbon, well, essentially, it is going to have an sp3 orbital for each bond. And that's because each bond is a single bond. So we have identified the types of orbitals, and now the only confusion that we can have is the fact that we have labeled sp2 and sp3 for the same carbon-carbon bond. Well, basically, this is an sp2-sp3 overlap, right? but the labels themselves, they correspond to each carbon atom, considering just the orbital coming from that specific carbon. So for the carbon-carbon bond, we simply have an overlap between the sp2 orbitals from carbonyls carbon and sp3 orbital coming from the methyls carbon. And now let's identify the bond angles. We already know that carbonyls carbon experiences trigonal planar geometry, so all of the bond angles would be 120 degrees based on the VSEPR theory. For the methyls carbon, since we have a tetrahedral geometry, all of the bond angles are going to be equal to approximately 109.5 degrees. So we're just going to label one of those angles, 109.5 degrees. And that's it. Let's label our answers, and thank you for watching.